This conference will now be recorded.
Okay, good morning all. We are discussing about linear block code, and last class and the previous classes we have studied how we can generate or construct that linear block code, NK linear block code, and see what is meant by the generator matrix and parity check matrix, P submatrix, etc. of a linear block code. And later we have seen that syndrome decoding, that is how we can decode using the method of that syndrome decoding. And before that we have also seen that the error detection and error correction capability of the linear block code using the parameter minimum distance d minimum. We can easily find out how many errors can be detected and how many errors can be corrected using that particular code we have generated. Okay, next is next we will like to see that another method of that decoding here in this slide, explaining that the content we have already discussed, that is NK block code. And for that there will be a block code or code word of length n and 2 raised to k code words. That is, if 3 is the message bits, number of message bits in a particular message, then there will be 8 code words, that is 2 raised to k code word. And how it is related to that Galois field GF2, that is we are using that mode to addition here, and that code word can be generated by multiplying the message with the generator matrix. That is, in this particular slide that another some other letters are used to indicate that message. Last class we have used that x equal to m into g. Anyway, here this v represent the code word and u is the message word and g is the generator matrix, and the dimension of each is represented here. The dimension of v is 1 by n, and u, that message word, is 1 by k, and generator matrix has the order of k by n. And later we have seen that error vector, and we can see that here that in this that r is represented the received vector. Last class we have represented it as y, and we can see that in the last class we have represented it as y equal to x plus e. Here r represents the received word and v is the transmitted word and e is the error vector. Then we have seen that syndrome is equal to y into h transpose. Here it is represented as r into h transpose, only that representation is different. That is we have seen the last class. Then we are going to see how we can decode using the method of that standard array. I will explain explain this standard array decoding with the help of an example. We can take an 6-3 linear block code. 6-3 linear block code, that is n equal to 6 and k is equal to 3. That is, each message is having length 3 bits and the corresponding word code word corresponding to each message is having length to 6. This we are generating a 6-bit length code word corresponding to each 3-bit message word. Okay, then here it is the generator matrix of the that particular 6-3 linear block code, and corresponding to that it is generated the code word. The code words are given here, that is here 000 000 000 001 011, like that 8 code words. It is, once we have got the generator matrix, we are able to write the complete code word. Here the I am not going to generating this, the method of the generating the this code word. We have studied this. And anyway, corresponding to that given generator matrix, the code words are written here. There are 8 code words. Okay. Then in standard array decoding, we are constructing a table here. First step is write the code word as a first row. Here, each 6-bit length bit sequence represent the code word. It is here there is a spacing shown in between these 3 bits. That is, anyway, this complete 6-bit sequence is the code word. Therefore, 6 zeros. It is the first code word. Then second code word is 001 011. Then third code word is 010110, like that. 8 code words that is in the shown in the previous slide, which is generated using the generator matrix. Okay, first step is write the complete code word as a first row, and here the first code word is 000. That is, to construct a standard array, place all the code words in the first row starting with the all 0 code word. Okay, this the place all the code words in the first row starting with the all zeros code word. Then the number of rows present in a standard array will be 2 raised to n minus k. Therefore, we can calculate, we get it as 8 rows. That is, then the complete standard array, there will be 8 rows. We are going to write that elements in these remaining 7 rows. It is that standard array is a table, and the first row is the all complete code word. Here there are 8 code words that is written as the first row. That is, here each 6-bit sequence is the code word. Okay. Then next step is choose a minimum weight n tuple from the remaining n tuple. That is, here n, we have n equal to 6. For that, n tuple means the bit sequence which contain that zeros and ones, total in 6 numbers. So for n tuple, choose a minimum weight n tuple from the remaining n tuples. This we know we can generate as much number of n tuple with that zeros and ones. Here only 8 we have written, which are our code words corresponding to that generator matrix. Then here next step is choose a minimum weight n tuple from the remaining n tuples. Therefore, here already all 0 code word is written. That is 0000000. Then we next one is that which is having minimum weight n tuple is which consists a single one, a one, and the remaining bits are zeros. Therefore, 5 zeros and ones. It can be like 1 0, first bit is 1 and the remaining bits are zeros, like that. Anyway, the remaining n tuples with the minimum weight is a 6-bit sequence which consists of 1 0 and the remaining 5 bits are zeros. One bit is 1 and the remaining 5 bits are zeros. Therefore, initially we can select this particular n tuple 00001. Okay. Then we have selected this as the n tuple. And write that particular n tuple below the all 0 code. That is in the first row. Remaining n tuples, and we will have to select the a minimum weight n tuple. Then we have written in the first column. This n tuple is called the error pattern. Then next step is add the error pattern to each of the code words in the first row to form the second row. Therefore, next step is add this 0, 0, 0, 0, 0, 1 to the remaining elements in the first row. That is the elements, remaining 7 elements of the second row. Therefore, here 0, 0, 0, 0, 0, 0, 0, 1, 1. Here will be the third bit will be 1. Then fourth bit will be 0, 0 for 0. Then fifth bit 0 plus 1, 1, and sixth bit 1 plus 1, 0. Like that. Add this error vector which is written here to the remaining 7 elements of the first row and write just below each element. That is, here add these two and write just below here. Add the error pattern to the first code word. Here the addition is mode 2 addition. Then here we get the element here as 0, 0, 0, 0, 0 plus 1, therefore 1, 0 plus 0, 0, 1, 0 plus 1, 1, 1 plus 1, last bit is 0. Here we have using mode 2 addition. Okay. Then next is add the error pattern to the next code word. Then write the result just below that. For first 0, 0, 0, 0, 1, 1, 0, 0, 0, 0, 1, 1, 0, 1, 1, 1, 0, 1. It is by adding these two, we can write the next element in the second row. Like that, we can complete the second row of this standard array. Okay. It is here. Initially, we have selected a n tuple which is having the minimum weight, which is not included in the first row. Okay, here first row is actually our code word. Then select that n tuple. Then add. It is the error vector. Add that error vector to the complete code words and generate the second row. Here this particular row obtained is termed as coset of this code. That is, that coset is obtained by adding error vector with the code. We can represent as that coset is equal to E plus C. E plus C. C, I mean the code words, that complete code word. That is error vector and the first code word. Here it is actually, we can say by adding these two, we get this. Then adding the second element with the code error vector, we get the this particular element. Anyway, we can complete the second row. Then next step is choose another n tuple of minimum weight from the remaining n tuple. That is, we will have to check all the n tuples obtained here. That is, if here in the next step I have selected the error vector as 0, 0, 0, 0, 1, 0. Suppose this particular 6-bit word, this particular 6-bit word is present anywhere here. That is, if we add this particular error vector and any of the code word we have obtained, this 0, 0, 0, 0, 1, 0 is obtained anywhere here, then we are not able to write that in this first column. Once a 6-bit code word, a word is obtained, this particular word is anywhere in this table, it is we are not able to write in here. This we will have to choose an n tuple with minimum weight which is not present in this table. That is the criteria for selecting that element in the first column. Therefore, initially 0, 0, 0, then we can say a word with the minimum weight is which consists of a single one and the remaining bits are zeros. Therefore, 5 ones and zeros. It can be any combination. Initially, I have selected first 5 bits 0 and next is 1. Then generated its coset. The coset means the set obtained by adding the error vector with the code words, that complete code words. Okay, once that row is completed, we will have to select another vector here which is having minimum weight which is not present. That is, in this table there will be 64 elements. You will have to write the 64 elements here, and all the 64 elements will be distinct. Reason is we know there are 6 bit here. Therefore, 2 raised to 6, that much elements can be formed by using that zeros and ones. And out of that, only 8 are our code words. We are in the standard array, that is in that particular table, we are writing all the remaining combination, that n tuples, that is here 6 tuple. Okay, for that initially we have selected an error vector which is having the minimum weight, then add that error vector with the complete code word, and here each row we are generated is termed as coset of the code word, coset. Okay, then we can generate the second coset. Therefore, we have selected the error vector, that is the element, simply saying the element which is written in the first column, we have selected as 0, 0, 0, 0, 1, 0. That is that second bit is here from the LSB, second bit is 1, remaining are 0. Then next step is add this vector with the complete code word. This plus this mode 2 addition we have done. We are doing this error vector plus this code word gives the element here. This error vector plus this code word give the element here, like that. It is adding these two. We get this 0, 0, 0, 0, 0 plus 1, third bit 1. Then 0 plus 0, 0, 1 plus 1. That is here. That fifth bit 1 plus 1. We are doing XOR addition, mode 2 addition. Therefore, 1 plus 1 is 0. Then 0, 1, 1. Okay. Similarly, we can complete the complete code word. This hope that you have got the idea. It is writing the error vector here which is having the minimum weight, then add this element with the next code word that give the element just below that. Similarly, this plus this give this error vector plus this code word give the element here, like that we can complete. It is here we can see in the next step the element selected as the error vector is 0, 0, 0, 1, 0, 0. Then add this error vector with the each code word in order to complete that particular row. This I repeat, if this 0, 0, 1, 0, 0 is present anywhere here, we are not able to write here. By observing, we can see that 0, 0, 0, 1, 0, 0 is not anywhere in the first 3 rows. In the first 3 rows. That is why I have selected that n tuple which is having that minimum weight. Similarly, in the next row, that is that fifth row, 0, 0, 1, 0, 0, 0 is selected, and adding, we can complete the standard array. Okay.
This conference will now be recorded.
John, please.
ഫസ്റ്റ് ഇതിനകത്ത് മറ്റേ 6 zeros ഇല്ലെങ്കിൽ ഒരു വലിയ നമ്പർ എന്ന് വിചാരിക്കുക, എല്ലാം 111010 എന്ന് വിചാരിക്കുക. നമുക്ക് സെക്കൻഡ് കോഡ് 000 എഴുതാമോ?
Assume there is, I think there is not such a case. If all zero word is not a code word, we will have to write the first element here, all zero word. That is the step, that algorithm in order to generate standard arrays, write the n tuple with the minimum weight. If all zero word is not a valid code word, we can go with that particular in the first step. We will have to write an n tuple with minimum weight. We know for a all zero word weight is 0. If it is not present, we can write according to that algorithm. Here in all cases, normally that all zero word will be present as a code word, valid code word. Therefore we will have to choose any word that is n tuple with the weight 1. That will be the first error vector. That is that element which is we are writing in the first column. If all the elements, all the n tuples with the weight 1 is already written, we will have to go with the n tuple with the weight 2. That is that which consists of 2 ones in that word. Okay. In that is about the generating the standard array. Initially I have said that it is used for decoding of linear block code. Once for this particular decoding, we will have to generate this standard array. Then we can see how we can decode by making use of this standard array. That how here which is already we have discussed here. That is when all the n tuples of vectors of weight 1 are exhausted. Now we choose another n tuple of weight 2 from the remaining n tuples. Okay, that is there will be, in this particular case, there will be 15 n tuples. That is here in that array is not completed actually. This here first, second, 3, 4, 5, 6, 7. That is 7 rows are completed. Here the 7 rows are completed. There are 8 rows actually in this case. That is here all the n tuples of vectors weight 1 are exhausted. Therefore the next step is choose another n tuple of weight 2 from the remaining n tuple, and we can calculate it as there will be 15 n tuples of weight 2, and out of this out of these 15 n tuples of weight 2, already some are written here. Here it is having weight 2, that is an n tuple with weight 2. Here this, that is which are shown in blue color, they have weight 2. That is out of these 15, 1 2 3 4 5 6 7 8 9 10 11 12 already there in the standard array table. Therefore we will have to select the remaining that word which is having weight 2, which is not already in the there are out of 15 there are 12 already present in the table. Therefore we will have to go with other. For here it is selected as 1 0 0 0 1 0. Then the step is add with this code word, which is our code word set. Therefore here the 8th row, that particular coset is obtained by adding this error vector. We can represent as take it as error vector, this n tuple which is having weight 2. It is added to all the code words and we can obtain that 8th row. Okay, here this is a standard array for a 6-3 code. The rows in a standard arrays are called coset. I have already mentioned that different rows of a standard arrays are termed as coset. That coset is obtained by adding that error vector with the code set, that is E plus C. That C I represented, I am using that numeral C as the code. Therefore E plus C give the coset. Anyway, the rows in a standard array are called coset. Then the first element in a row of the standard array is called the coset leader. Okay, the first element, that is, actually we are writing that first element. The first element in a row of the standard array is called the coset leader. Then the coset leaders are exactly the correctable error pattern. Coset leaders, it is in each row is termed as coset. The first element in a row is called the coset leader. That coset leader, the coset leader are exactly the correctable error pattern. That is, that particular error pattern can be used to correct the error. Okay, we can see. Okay, we can see the received vector is 0 0 1 1 0. That is, we have received a n tuple, that is, which is having 6-bit length. It is 0 0 1 1 0. 0 0 1 1 0. It is not there in the first row. 0 0 0 1 1 0. That is our code word received. 3 zeros, then 1 1 0. It is not there in the first row. Means it is not a valid code word. In the syndrome decoding, we have seen that that if we multiply that vector, received vector, this particular vector, we will not get a zero vector, which means it is an errored vector. It is not the actual transmitted word. Some errors occurred. This here it is the received word. It is not there in the first row. Therefore, it means some error is occurred. Then, according to this standard array decoding, check where is that particular vector present. That is, in this standard array there are 64 elements. Okay, out of that only 8 are valid code word. That is the first row. The first row is the valid code word. That 8 elements, we have only 8 code word, 8 messages and 8 code word. In this standard array there are 64 elements. Therefore means if you receive any other word, some error is occurred. Then according to this standard array decoding, check where this particular received vector is present. We can see it is here. That is in that third column. That particular received word is present. Therefore, from this we can conclude that the received vector R is decoded to be the 0 1 0 1 1 0 from the standard array. That is, actual transmitted word is 0 1 0 1 1 0. That is the method of decoding. That is, check where is that received word is present. Then that is, initially we can see it is not present in the first row. It means it is not the actual transmitted code word. It is not a valid code word. Some errors are occurred, and we can in this particular case that received word 0 0 0 1 1 0 is present here, which is represented in blue, and it can be decoded as, which is represented as in purple, that 0 1 0 1 1 0. Okay, like that if we we have received 001 101. That is, here we have given that received word is 001 101. If we go check for that vector, it will not be present in the first row, and here we can see here 001, and we can conclude that the actual transmitted word is 011101, like that. Okay, that's about that standard array decoding. I think that you have understood what is meant by that standard array, how we can generate the standard array, and how we can decode using that standard array. Here the disadvantage is more memory elements are needed for this purpose. That is, all the elements of that standard array will have to be stored. Therefore, it is not a better way of decoding. That is why we go for that syndrome decoding, comparatively very simple, and less memory elements are required. We can represent this in decoder, syndrome decoder, by a block diagram, and we can see how many memory elements are required there. Anyway, it is not a better way. Anyway, we can decode a linear block code by using this standard array. Therefore, it is termed as standard array decoding. Next in this particular slide, that is, we have already studied that syndrome decoding. That is H. Then from that syndrome vector is equal to E into H transpose. We have already seen this. And here one more element, one more point we can add here. It is once an element is identified in this particular standard array, the corresponding error vector will be the coset leader of that coset leader. Therefore, 000110, it is the received vector. Then the error vector is 01000. Therefore, then by adding the error vector with the received vector, we will obtain that corrected word. Okay, that is this. It is the received word. We can say Y or R. Then it is the error vector E. Then R plus E or Y plus E give this V or X. That is that actual code word. That is, once that element is identified in a in the standard array in a particular position, then the corresponding coset leader will be the error vector corresponding to that received word. That error vector plus received word give the corrected word. In that way, also, we can find that corrected word. Okay.